I'm Amanda Thomas, one of the CottonInfo team. I'm an RDO based in the Macquarie Valley, and I'll be helping facilitate today. This webinar is part of a series of extension and outreach project that's jointly funded by the CRDC, Cotton Australia and Cottonseed Distributors, and the Federal Department of Agriculture. These particular projects of greenhouse gases and encourage the best management practices to reduce them. Today we have the famous Chris Dowling speaking. He's run over 20 workshops in cotton growing areas in the last 18 months, and the material in the first two sessions will be based around those workshops. Chris has about 20 years experience working for Incitec Pivot, so he knows his way around a soil test and paddock and his presentation. And then we're going to go with typing in any questions that you have, type them in at the end. We can then record the webinar and then we'll distribute it on the CottonInfo site. I'll give you that at the end. And then we can go through particular questions that you've got typed in so that everyone will get to ask him a question or two. I might hand over to Chris.
Good afternoon, and thank you, Amanda, for that kind introduction. It's been a delight to be actually getting around the cotton industry and seeing the innovation and the progress that people are being able to put to the ground and keep the industry profitable. But this topic that we're approaching today is one that's a perennial. It gets asked about quite regularly, about how do we improve our efficiency of nitrogen. And as the title in this session, and obviously the government's understanding of the opportunity and the reason why this project was funded was there is a joint benefit in increasing the efficiency, particularly in the irrigated cotton segment, because the environmental impact goes along with it. And that's in recognition that one of the larger loss processes in the inefficiencies is the gaseous emissions pathway by which what we've identified now, a large proportion of the nitrogen is lost, hence the low efficiency or the lower efficiency. So this morning this first section, we're going to talk largely about the the environment in which cotton's grown and the types of factors that that drive the cotton crop to need nitrogen. And the challenge ahead of us in doing this is the responsible use of nitrogen fertiliser to try and get both an economic and an environmental outcome. And it is possible, but in some cases we're getting a crossover of messages where people are driving yield and profitability, and the environmental side, because there's no dollars in it at this stage, gets left behind. So increasing profitability, that's what we want to talk about, because unless we're profitable, then there is no cotton industry. But increasing nitrogen efficiency is important as well to keep costs down, and understanding how we can progress forward with higher yields with higher efficiency. And of course, high efficiency can come from two areas: by either increasing the yield from the same rate that we're applying now, or maintaining yield to maintain yield from the current rate. So, we can either reduce the rate or increase the yield. Both are important ways of going about it, but deciding on which one is possible and which one is right for what circumstances is part of the challenge. From the environmental impact, we want to reduce the gaseous emissions because they are part of the low efficiency. They're the loss that doesn't go into yield. And we can do that also by controlling getting control of nitrate that's floating around the system. So we've got direct emissions, as we know from the field, but also identified through Ben McDonald's work on uncontrolled nitrate in our water systems on cotton farms that are emitting nitrogen as well. So getting control of nitrogen is what it's about. In doing that, we've got to know where it's coming from, why do we need it, and what's an adequate amount. So in this first session, this is the first of 3 sessions over the next 3 days, what I want to do is look at the key drivers of yield and hence nutrient demand. Where do the nutrients fit in growth and yield processes? Growth factors that affect nutrient demand, the effect of where you're growing cotton, like the agroclimatic variables and seasonal weather patterns on demand, and the effect of soil on nutrient availability. Now, they're all trying to get some feeling for ultimately why do we use the rates that we do, and why do we use rates in excess of what the efficiency would say was adequate. So, you know, if we're going to improve efficiency, we've got to do it in a way that it doesn't come at the expense of yield. In Australia, obviously, we're growing cotton across a very diverse group of climatic soils and other production areas. So, you know, there's a whole heap of variables. There is not one thing that cures all. If we were to do one thing and then everybody would be right. Given we've got cotton growing from the humid subtropics and into the tropics, if you take into account what's grown in the Burdekin, and right through to the temperate areas of the southern cotton growing regions, there's a whole heap of challenges, such as summer rainfall. Summer rainfall is a potential to interrupt nitrogen efficiency, and of course summer rainfall is a lot more prevalent in the northern and eastern parts of the cotton growing areas than the western and southern during summer. That's just a fact of the way climate works. We need to take that into account because it changes our risk profile of certain practices based on, you know, the emissions we're talking about are driven by generally waterlogging. By the same token, we have soils, quite a deal of variability in soils, and obviously soils that don't drain as well in a climate that has a high probability of intense summer rain during a cotton production season have a higher probability and a higher risk of losses of nitrogen should it be present in the soil at that time. So you add all those things up and you say, well, you know, practices can't be consistent right across all those areas based on the risk and the you know, the probability of getting an event that might cause an inefficiency such as that's driven by nitrogen emissions losses from the nitrate pool. So, you know, look at that diverse production. It also actually has an impact directly on the possibility of yield. And if we have a look at the you know, the key drivers of cotton production, these would be the summary of the handful of things that really we have to manipulate when we're talking about the main game in growing cotton, which is really, as that bottom equation says, radiant energy to bioavailable chemical energy, sugar, or in the case of cotton, through to cellulose, just a complex sugar. And what we do as managers is we manipulate this group of parameters, the factory if you like, taking light, trapping it in carbon dioxide from air and water from what we put on and create carbohydrate. The efficiency with which we do that is the thing that drives the nitrogen demand. So, you know, some of the levers that we have to lever up the yield or reduce the loss process are one and the same. Water is one of those that is key to this. So, you know, across a diversity of areas, we have variability in light, we have variability in water, we have a variability in light energy or even, you know, solar energy, which creates temperature, thermal energy. And all of those things are important in managing the crop for efficiency. One of the other challenges with cotton is we've got to recognise that it is a little bit different to a lot of other crops in that it has an indeterminate habit. In other words, there's intense competition between plant structure and reproductive structures for resources during the growing period. That makes the nitrogen supply need to be meted out in quite a in an orderly fashion to make sure that we keep those plant structural or dry matter growth and harvestable growth in a reasonably good relationship to make sure we don't grow big plants with no yield. We want as small a plant as we can with as much yield as possible. It is actually a perennial plant that we grow annualized, and in doing that we always need to go close to the edge in managing it to make sure that there's not too much nitrogen there to make it think it is a perennial, and we can actually harvest the crop and finish it up with good quality material. And the other challenge when it comes to managing nutrients like nitrogen is the main end product contains very little nutrient, or if any at all. It is in the seed, and it's the relationship between the lint and the seed quantity in any harvestable part that makes it a little bit more difficult to understand that relationship between removal and profitability. If we look underground, also we've got to acknowledge that the cotton roots don't grow like cereals, and there are some differences. And this obviously, nitrogen and nutrients coming mostly from below ground, then the effect that we have on the roots has an effect on nitrogen and other nutrient uptake. So this is US data. I haven't seen it being measured in Australia, but I imagine cotton roots, other than difference in soil types, which will change these to some extent, but the generalisations would probably hold. So, you know, cotton root density under favourable conditions is not as dense as wheat, barley, corn, the cereals. We would know that. That would not be a difference, but there would be differences between soil types. Those that are heavily textured probably have even less density per square metre, per cubic metre of soil than lighter textured soils. Growth in drying soils. So as things dry down, cotton roots tend to be poor compared to wheat and barley. Growth response to frequent irrigation, slight increase in cotton in the surface roots, dramatic increase in these other crops. So there's differences, and this means there are differences. It causes differences in the way that we need to look at nutrient access in cotton, and more particularly the way that we might use nitrogen in cotton, because the root systems are not the same as some of the other crops that have commonly been grown, and a lot of our practices have grown up based on the cereals more so than cotton. If we go back and look at just the variability in things that drive this cotton factory, light is something that is quite different across quite a bit of the cotton industry because of the variation in latitude in which it's grown, and it changes seasonally. Now, light is the energy thing that drives the ultimate top yield that you can grow of any plant. If you think about where the highest yields of wheat and maize and all of those types of crops grow in the world, they are from areas that during summer they have very high light intensity and very long days. So you're talking about the higher latitudes. So the types of things that is a factor that affects the amount of nitrogen that may be required in any one area, because the length of light, if it was unlimited, then we would have very high yields, but we have limitations, and in particular cotton being a summer growing crop, then the longest light generally, as you can see, the average daily exposure is a lot more in the south in summer than it is in the north, and that may be one of the limitations to total yield and therefore total nitrogen required in any one area across the whole across the area that it's grown. On a excuse me, on a shorter term basis, you can see this is a plot of accumulated solar radiation at Griffith, probably the southern end, and Emerald at the northern end of our cotton growing areas. And you can see, and this is 2013, but this is not atypical of a lot of seasons in these areas, where in the south the areas start lower in solar radiation across the board, but about the time we get to flowering in December, they cross over, and those southern areas the solar radiation gets more. And then in the northern areas, because of the effect of cyclones and summer storms, you can see I put a circle around there in Emerald, the tail end of a cyclone coming south, a cloudy period, and there's a drop-off in solar radiation late in the season that can obviously affect yield potential. Just purely based on the totals, you can see that that the southern areas have a higher total solar radiation in general. Well, of course, the light has to be controlled or looked at in the light of the amount of heat, because heat actually controls the rate at which the plant develops. So if we have areas that have faster development than other areas, excuse me, for the same yield, it is quite possible that they need higher rates of nitrogen relatively to be able to produce the amount of yield that's required in a shorter period of time. So if we look at the spots across Australia, we're really that cotton's being grown, it spans about 3 different heat zones when we look at the October to April area. And if this is taken into account in decision support around nitrogen, that we have the hot areas such as Emerald, Burke, and the St George. We have the more moderate areas which cover the majority of the central cotton area, and we have the more eastern and southern areas that sit in a heat situation that is slightly different to the others. So the rate of development obviously is quite different, and when you actually plot that, the time to 60% open bowls on average for 3 locations or 3 areas that represent those, you can see is quite a vast difference in the accumulation of heat. So to grow 10 bales in hay, you do it at 10 day degrees per day, whereas at Emerald it's 40% faster. So given that in the hotter climates it's required 40% faster to produce the same amount, then the concentration of nitrogen to do that in the soil needs to be higher. When we look at productivity on a daily basis, you can see it's a different view of things. And this, I throw this in just to show you that just because it, the average yield of a district is lower, somewhere like Emerald, having a yield last year of the 9.5 bales average for the district, doing it in 145 days, they were able to produce basically 15 kilograms of lint per hectare per day, as compared to Moree at around 19, and the Griffith area, even though it had a higher average yield, it took longer to do it. So on a daily basis, you know, those quicker areas are not necessarily, they might have lower yields, but they're not necessarily less productive. So look, there's, you know, whenever you have a look at, excuse me, a yield map, you always identify areas with potentially higher yields. And it is quite common where if an area is yielding 15 bales, to be able to identify areas in those fields that might be doing 18. And of course the question is, how much higher can we go, and can we push that average? Well, ultimately, you know, light extinguishment under the current canopy structure we have with leaf shape and canopy shape, it would appear that light extinguishment, in other words, we can't get any, you know, leaves become inefficient because there's too many of them. Yield tops out around the 20 to 25 bales. So we're not there yet, but there is potential there. But the other thing we need to be very careful of is we look at the nitrogen uptake per bale as it currently stands in relation to the yield achievement. You can see we're dropping off the efficiency as we go up that yield ladder. It's the law of diminishing returns. The harder we try and get that last few percent, the more it costs us. And that is showing up with the nitrogen equation at the moment. So, you know, the amount of nitrogen required to grow 6 bales is about 11 or 11.5 kilograms of N per bale. But when we push out to 15 bales, you know, we're looking at around the 18 or 19 kilograms of uptake nitrogen per bale. So we've lost, you know, a large amount of efficiency. The question is there a way of actually improving that situation, or as we push up, we make sure that we're not losing more efficiency than we need to? One of the other limitations that was identified, or one of the other things that is in that whole efficiency of nitrogen, is making sure other nutrients are not limiting. And, you know, on the left-hand side here, you can see that nitrogen is a large uptake for a cotton crop in that top graph, but also things like potassium and calcium are equally large in the quantities that is taken up by the crop in total. Not so much for potassium, magnesium and sulfur, and even less for the trace elements, of course. But we need to make sure that, that those other elements are not missing or not limiting, as that will limit our nitrogen use efficiency. And if we limit nitrogen use efficiency through those nutrients, it means we might be fertilising for a higher yield. If we undershoot because the crop can't grow because of another nutrient limiting, then the nitrogen is out there at risk of loss and we will come up with a low efficiency figure when we start to look at the end of the season. So, you know, which are the other nutrients that are at risk? And, you know, we need to go through that exercise and identify that on a soil by soil basis as to what that might be. So just in looking at the data that's coming back from plant tissue analysis, you can get a very different view from soil analysis. But you know, ultimately, the plant tissue at around flowering is probably quite a true image of what's really happening. This is a survey of leaf pea data across all crops in 2012-13, and what we have here at around flowering, the 600 to 800 day degrees, you can see there are a few crops here that, based on our current understanding of what the adequate level is at that stage in the leaf, you'd say probably 2/3 to 80% of the crops look quite adequate, and some of the other ones down here were looking a bit sad. So we still have phosphorus deficiency out there, and some of these crops, particularly the 2012 ones, were affected by waterlogging around that time. So it may reflect the effect of waterlogging on root growth, on phosphorus uptake. But by and large, yes, we have to be careful about phosphorus and make sure that's covered off. As to how and why and when, that may be a different thing for the researchers to better describe how we get more phosphorus in than we may currently be doing with cotton. Sulfur is another one that we get asked about. You can see, based on the levels from literature review, in general the cotton industry doesn't have a lot of problems with sulfur deficiency. There's some early season signs there in young crops that may be some problems in some years based on limited root growth and not finding deeper sulfur, but generally sulfur would appear okay. Some of the trace elements, again, boron's one we get concerned about in cotton, but when you look at the critical ranges that are given in the literature, occasionally we see a boron that might slip slightly below that. Maybe again based on root architecture, but generally, by and large, the large majority are adequate for boron. So, I think we've got a pretty fair idea of which nutrients are likely to be limiting. And in the absence of data, when we get close to the given soil test critical levels, replacement rates is not a bad place to go. So looking more closely at nitrogen, the question is how much is enough? And really there is no answer to that in any one season. It is a variable, and the key driver of that is yield. So, the actual amount that you require depends on the yield and how accurately you can predict what the yield might likely to be, or how able you are to manipulate the yield across the season into a position that is reflective of the nitrogen that you've used. The total demand is split up between roots, stems, leaves, and seed. Hopefully the majority of it's in the seed, which means it's going to produce lint. The other part, when we look at the balance, is whether what's not in the plant, where does that end up? To meet that demand, we need soil supply, and it can come from three basic places. Mineral N that was in the soil at the time that the plant was sown, mineralized N, which can come from two fractions. One is the breaking down organic matter from the previous crops, and from the humic fraction in the soil. The last one is usually what we see as the deficit, where mineral N and mineralized N can't meet the requirement of the crop. Then we add it as fertilizer N. Now each of those pools has different efficiencies and uptake efficiencies and losses. Probably the most efficient one is the mineralized N, followed by the mineral N, and the fertilizer N is one that can be quite variable, and it's the one where we have the ability to manipulate that one across the season, starting with pre-plant and to in crop. The other two we have to take in as given, and their efficiency really depends on our water management. So around managing these pools, we've got to recognise the size of them and the efficiency of them, and then manage the nitrogen fertiliser to get overall efficiency based on that. How good's our current management? Well, really until the last two seasons we probably would have said we don't know. But the time's coming when these things are going to be a lot more easy to manage. If you'd have asked somebody 10 or 15 years ago what was their average consumption over 12 months, fuel consumption of their car, they would have probably looked at you and given you a guess. But in this day and age, with these sorts of meters in cars, most people can give you their consumption, particularly for the last week or the last month, or the last tank full anyway. It's probably not far off being able to see these sorts of things done on the go at harvest. If not, it certainly is quite feasible to have a look at efficiency factors such as, you know, the partial factor productivity of nitrogen, the yield divided by the nitrogen rate used, to see that coming up pretty easily. And the question mark is, how well are we doing with those? And is there a need to improve? Is there a capability of improving? And what might that happen? In doing that exercise, one of the first things you see some people do is just to go and willy-nilly and start changing their fertilizer rates or split applying or changing products. Probably the most productive way, if you want to improve nitrogen use efficiency and reduce nitrogen emissions, is try and identify the most likely causes of those low efficiencies. And if you do that, you'll probably find they come from one of or a couple of these 6 common causes of low efficiency. One is basic. The first one, and is probably the most common, is the supply of nitrogen is greater than the demand. In other words, we oversupply. And that oversupply amount is then out there with a probability of loss, and the most likely when you're in irrigated cotton in clay soils that there will be a degree of loss. So better matching supply and demand is probably one of the keys to increasing nitrogen use efficiency and reducing emissions. Why do people oversupply? Possibly because they're worried about the loss in profitability of undersupplying. So this is a process of trying to do it by small amounts to make sure we get control of that, because there is plenty of evidence to say that if you undersupply, then there is a yield and profitability penalty. One of the other ones is inefficient uptake, and this is probably why people oversupply, because they're counting on there being an inefficiency. Well, it comes down to why is that inefficiency there, and can that be directly attacked? And the inefficiency of uptake might be from things like poor watering management. Are we waterlogging the thing for too long? And why are we doing that? Is that because we've got poor structure in the soil that's related to management of soil engaging processes during the fallow period? So there's a whole heap of things that cascade into having an oversupply and inefficient uptake. But what's the primary cause? It's better to attack the primary cause than necessarily try and attack the what evolves as a result of that primary cause. The other third situation is applied but temporarily available. It's unusual, but planting into heavy wheat stubbles, it is quite possible for nitrogen to be tied up and released later on. That's not something necessarily that might affect an efficiency. It can be applied or mineralized from the soil, but lost from the soil. And this is where it may be inadvertent through a weather event, or it can be as a result of irrigation practice. But we've lost it from the soil, we've applied it, lost it, and then reapplied more. The total amount of N applied doesn't match up with the yield that has actually been achieved. Available in the soil but not taken up. So is there a compaction layer or some other thing stopping it from being taken up? Or it's taken up in the biomass and not transferred to the harvested produce. And this would, the case in count with cotton would be that it goes into the plant but it doesn't end up in harvested yield. In other words, we have a lot of boll loss or unharvested cotton, or it's just tied up in the biomass that didn't go into yield. So they're the general I suppose, as I said, drivers of the difference or the need for, I think about different management for different locations across Australia where cotton's grown, and different seasons, because it is quite common for areas, particularly in that intermediate zone from the Darling Downs down to about Narrabri, to get northern summers. We end up with a cloudy, low light summer, or to get southern ones where it's clear, light and hot. We get variations season to season. It's, I suppose, the challenge in trying to improve efficiency is in recognising the types of drivers of yield we have in any one season, and even within the season, and having management in place to be able to roll with the punches that we're given. In large part, that would seem to mean that not putting all our eggs in one basket, and having a multiple application strategy for nitrogen in particular, that gives us some ability to actually manage for the type of season that we're getting. In other words, increasing the nitrogen supply where the season signals say that we have a higher potential, either through light or heat accumulation, or a lower potential based on cloud and a cooler season. So identifying the under limitations is key to understanding what those adaptations might be. Excuse me. And the starting point for trying to manage for higher use efficiency and reduced emissions is figuring out where are we now. It would be a crazy thing to figure out that you're currently producing 15 kilograms per kilogram of N, and thinking it would be a good thing to do to improve efficiency. If we're already got good efficiency, then we need to concentrate on some other part of the production. But by and large, survey data would say that nitrogen use efficiency in cotton is not, in general, in the range that we would say is adequate or up to best practice, and there is a need or there is an opportunity to improve it. Seasonally, yes, there's going to be differences. Last season was a very good season, and the efficiency was pretty good based on uninterrupted watering patterns and a whole heap of reasons why last season was probably better than the season before. So this is a long-term commitment, not a short-term one, and it's a road, it's a pathway to a better place rather than a destination. So in the next session, what we're going to explore in more detail are the factors affecting nitrogen demand, availability and use efficiency, the major loss pathways, the size and importance for nitrogen, some measures of nitrogen use efficiency and what are adequate numbers. So, if we want to go out and improve it, we need to know where we are now and the range that we're likely to encounter. Some of the tools for managing nitrogen use efficiency, explore those, and just look at some of the best practice nitrogen use information. So my time's done, probably run a little bit over, but I think it's important to put in place some of those drivers. And I'll open it up to questions. Amanda, over to you.
Hi, if I drop out, guys, just pop the question and I'll hand it over to Jon. I'll try and stick with it as best I can. If anyone's got any questions, do you want to just type them in and I can read them out for you? I've got a few questions. Get it going. I just wondered about when if growers are, are working out their nitrogen fertiliser use efficiency. Does that take into account sort of what's in the soil already and what's there left over? Or is that just something that we're just looking at the lint divided by the nitrogen fertiliser?
Did you get that, Chris?
John, I think everyone's become unmuted, and that's the feedback.
Oh, okay. I'll let Chris continue.
A little bit, depending on the variety. 74 has a higher seed nitrogen but a high turnout. So what's happened is across the varieties, generally we recognise now it's about 12 kilograms per bale in the high yield situations of what's being removed. Now, how much of that actually comes from which pools is dependent on a range, and the overall efficiency depends on a range of variables. To take into account the mineralisable nitrogen and the effective structure on efficiency, there's a crop rotation factor that goes into the development of an efficiency. So higher efficiencies from where cereals are grown in rotation with cotton, or you'll have a longer fallow period. Obviously, from where you've got pulse crops involved, you've got a nitrogen that's going into the legume pool, which I said was probably more efficient than the fertiliser pool. And so you get a higher efficiency from having a greater proportion from the legume component than from the fertiliser N applied. And then there's other factors such as compaction, soil type, location, all get grouped up together into an efficiency for a particular situation. So there isn't one efficiency, but generally, if you're budgeting on it, it generally comes out somewhere between about 22 and 30 kilograms of nitrogen per bale, depending on the circumstance. So if you had a multiple year rotation with cereals coming into cotton on a medium clay with no compaction, and you're growing it in the central cotton growing area of Australia, then you probably have an a requirement for 22 kilograms per bale, versus something that was a little less friendly, might be up as high as 30, 32 kilograms per bale of requirement. So, just to finish that off, if we're saying that 12 kilograms is removed in the seed per bale on average, we're talking about an efficiency somewhere between an overall, and this is the whole of pool, this is fertiliser, mineralisable nitrogen and mineral nitrogen in the soil, we're talking about an efficiency of somewhere between about 30 and 50%, depending on the circumstance.
Okay, thanks for that. We've got a question here. To what extent does soil salinity tend to affect the water and N uptake and therefore nitrogen use efficiency in the soil?
Salinity primarily affects obviously water uptake, the ease of getting water out of the soil, and nitrate is taken up in that water, in that stream of water. So anything that affects water uptake affects nitrogen uptake. So what you need to be able to do is define the level of inhibition of water uptake, and even though nitrogen might be present in a layer of soil, if water cannot be extracted from there, neither can the nitrate. So there is a need for some discounting according to the water availability limitation that may be experienced. So cotton's a pretty tolerant crop as far as salinity is concerned, and I would say generally it is really only layers below 60 centimetres, other than really saline soils. Generally I only see the types of ECs that you require to restrict water uptake below 60 centimetres. So, you know, it may only be of the crop's extraction area. It may be only a 10 or 15% out of a small layer of the soil that's actually restricted. The only way to get a reasonable idea is to do a segmented soil sample to understand where the critical values or the critical ranges cut in, where water will be potentially restricted. And have a look at that based on the whole profile, or assess that in relation to the whole profile. It may not be significant.
Okay, well, there's a couple more questions there, Chris. One is, do you believe that we could find ourselves in a situation where legislation dictates the use of N fertilisers on farms?
Look, there are situations obviously throughout the world, and examples within Australia where that has happened. It is always a potential where there is a impact from the use of that input that that has a large effect on the community, the environment. That is always a potential. I would think that generally in situations where there is an ability to have a win-win situation, such as we have here with nitrogen, with improvement of nitrogen use efficiency, having a potential economic gain to the farmer as well as an environmental gain, progress towards that and a measurable progress towards that would deflect any need for that type of approach. It's a little different to the situation with, say, nitrate that might be leaking into soil and then going out to a sensitive water body, in that the emissions or stopping emissions, which are largely what's concerned about in the cotton industry, is something where when it happens it's an immediate saving. Where nitrates might be leaking into the environment and it's in the soil, it may take 20 to 50 years for the effect of the previous 20 years to actually work its way through the system. So this one's one where you can't say it would never happen, but to be able to demonstrate from the same amount of nitrogen that you got more yield would indicate that the crop took up more, it emitted less, therefore it's been a win-win basis, and hence this project moving forward with a focus on efficiency, because it is a win-win situation.
Thanks for that, Chris, and thank you, Hugo, for posting that question. We have one here from Richard, Chris, do you have a magic number as to what percentage should be applied up front in your budget, and what is your reason for that?
There is no magic number. In trying to improve efficiency, we need to recognise that any nitrogen that is applied ahead of demand by the crop, or uptake by the crop, in other words, making it safe from losses, is at risk of being lost and creating a lower efficiency and higher emissions. So in any situation, it comes down to an assessment of the risk potential of the loss. So, you know, we'll talk a little bit more about denitrification, the process that we're mostly concerned about in the next session. But in summarising it, we've also got to temper that with having enough nitrogen on there that we can grow the crop profitably. The less chance you have of an unexpected weather event interrupting the period before first flowers, the nitrogen, the ability to get nitrogen on before first flowers, the more I tend towards backing off on the pre-plant